So, all right, so let's do this. All right, so we're going to be talking about section 1.3 exponential functions. All right, so here we're going to, I don't know how much of this you know, so I'm just going to assume 0. So if some of it's review, that's fine. It may not be review for somebody else. Okay, and if not, even if it's review, sometimes it's nice to go a little bit slower. All right, so let's talk about a definition of exponent. A to the n means a times a times a times a n times, right? We call a to the n an exponential expression. So if it's just by itself in its expression, if it is equal to something, we call this an equation. So this is an expression by itself, and an equation if it's set equal to something. We call a here the base, right? So a is our base, and n is the exponent. And so here, this is what happens if n is a natural number. And so these are things you know how to deal with. Now, if n's a positive integer, so here if I have 0 or negative, so a to the 0 is 1. And the reason we do that is here if I have a times a times a times 5, this is 5a to the third, right? But if I have 5 and I want to write what a is, I want 5 times 1 because 1 is the multiplicative identity element. That's a real fancy math term, means it doesn't change anything of 5. And so 5 times a to the 0 means I have 0 times a. And so that's why a to the 0 is 1, is because of the multiplicative identity. Now, do you really need to know that? Not really. Just remember a to the 0 equals 1. Anything to the 0 equals 1. A to a negative number, so a to a negative natural number is just 1 over a to the n. Okay? So you can just, it's divided by instead of multiplied. So that's what the exponents are. And so we have all these laws of exponents. So here, if I multiply two a's together, or a to the n times a to the m, that is a to the m plus n. And here it's like, 3 to the 4th times 3 to the 7th. Well, that's, you can just add that up, and that becomes 3 to the 11th. And another way of seeing that is I could just write this out. I could just add 3 4 times, and I could have 3, 1, 2, 3, 4, 5, 6, 7. And if I count it all up, this is 3 to the 11th. So that's kind of like how that falls down. If I have a to the n over a to the m, I have a to the n minus n. And so here, notice here I get a to the minus 2, or 1 over 25th. But notice here I can cross off 4 5s up top, or 4 5s down below, and get the same answer. So this works out to be the same. If I have a to the n times m, we have a to the m times, so here if I have one power raised to another, so let me make this a little bit more clear. I mean, this is written as clear as, but if I have a to the 4th, right, it'll be the same as a to the 3rd. And that's because I'll have 2 3s, 2 3s, 2 3s, and 2 3s, and altogether it'll be 8 3s. So here, if I pull it out, so when I do that, I multiply. Here I can put it in. I can distribute it in parentheses, either this way or this way. So to each multiple, or even to the division. And here, if I have that, I can flip it. And here I give you examples of everything. Okay, so technically, the first page, you actually don't have to make any marks whatsoever. It's all just a reference sheet for you guys. All right, so let's look. So this part is where it gets kind of new for some of you, and definitely new for other parts of you. So here, let's say x is rational. So I'm going to take a to the x, and oops, this is not correct. This should look like a to the p over q. I think that divided by q didn't get really clear. So make sure it looks like this, or you understand it's this. So make a little note on your paper. I'll have to fix that. So if a is p over q, it's equal to p over a to the p to the qth root, or the qth root of a to the p power, right? Because remember, a to the half is equal to the square root of a, and a to the 1/3 is equal to the cubic root of a. So a to the 2/3 would equal to the cubic root of a squared, or the cubic root of a then squared. These end up giving you the same thing. Now, if x is irrational, x is irrational, then we just take the limit as x of r goes to x, where of AR, where x is rational. And so here, let's pretend we had pi, which is 3.14159, and so forth, right? And so how would we take this limit? Well, we just do it numerically. We'd take a 3.1 and then 3.14. That's rational, and that's rational. And just keep adding up the digits. And so we don't know exactly what the number is, but we can get really, really, really close. Okay? And technically, there's a theorem out in mathematics out there. This is kind of, I'll explain the theorem in 2 seconds to you and explain and make it make a lot of sense, but and then I'll break your brains for a little bit. So between every two rational numbers, so if I have a rational number, there's an irrational number. Okay. And between every two irrational numbers, there's a rational number. And then the proof's actually really quite easily, right? Easily done. Here, if I have two rational numbers, they'll truncate at some point, right? There's some sort of truncation. They'll differ. You just keep wandering down. So if I have 3.1, 5, 6, 7, 8, you just keep wandering down this until they differ, right? Let me do the two irrationals. And I had 3.1, 4, 6, 9, 2, 1. So you just keep wandering it down until they differ. Once they differ, you just truncate the larger one. And there is your rational between two irrationals, right? You can do the same thing for rational numbers, or between any two irrational numbers. You can have any infinite string of random numbers after that, and that will produce it. Oops, I'm on the wrong layer. And so you can get excessively close, but the amount of irrational numbers to rational numbers, say if I took a dartboard that just had randomly displayed rational and irrational numbers and I threw the dart at it, the chance of me picking a rational number is 0%. It's not close to 0, it is 0%. There's just so many more irrationals than there are rationals, even though I can prove between every irrational there's a rational, and between every rational there's an irrational. It's kind of weird. I wouldn't worry too much about that. That's just a fun math note. So, but honestly, if it's irrational, you just get it as close as possible. That's how we deal with irrational exponents. So this part might be new to some of you, right? Or at least the rational part. You take the limit and you're taking values which are strictly rational as you get closer and closer to your irrational number. Okay. So that's all the properties of exponents. This part might be new. The other part might be old. It all might be new. I don't know. And it might be old. All right, so here's an exponential function. So an exponential function is we're going to take a and we're going to let x be the exponent, right? Where it has the domain of all reals and the range from 0 to infinity. And we'll let this line be a horizontal asymptote, which once again is where a graph approaches but never crosses. So if a is greater than 0 or greater than 1, if a is greater than 1, our graph will vaguely look like this. So it vaguely looks like this. But actually, let me show you a whole bunch of these all at once. And this point will be 0, 1. And then here, let me do another one here. And this point will also be 0, 1, because it doesn't matter if it's above or below, but then it looks something vaguely like this. So it flips. But let me graph a whole bunch of these real quick for you with Desmos. Desmos, let me show you these. Calculator. All right, so let's graph like, I don't know, to the bx. I'll put e to the x on there. We haven't talked what e is quite yet, but we'll go ahead and put that on there. I'll put 10 to the x on there. And I'll put like 1.1 to the x on there. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 to the x on there just for kicks. And I'll put 1 And so notice what happens here. Every single one of them goes to the point 0, 1. Now so here's 1 to the x, here's 1.1 to the x, here's 2 to the x, here's e to the x, which is a little larger than 2, and here's 10 to the x. And so the the greater than the base is, the more steep this curve is. So this curve gets steeper and steeper and steeper, right? And then here it flattens out, and then it'll here, but it never reaches 0. But the steeper the x, the faster it goes to 0. It never reaches 0, but it goes to it, right? And so notice this one takes a long time. And that. Now, if it's less than 1, so let's say it's 0.5 x, right? It looks like this, and that's because if I multiply a fraction, say if I take a half times a half, I get a fourth, right? And then a fourth times, and then times a half again would be an eighth. And so it gets smaller and smaller for the larger numbers of x. However, when I have a negative, 1 over an eighth is 8, and so it grows this way. In fact, this 2, and they're both in red, which is nice. This 2 and this half, right, directly mirror each other. They directly mirror each other. So here, if I drew in the mirror of the other one, say like 0.1 to the 10th to the x, this will directly mirror the 10. Okay. And so here, this will mirror each other. So here's how the exponential function looks. The domain of the exponential function, because you can put anything in as an exponent, is from negative infinity to infinity. The range is between 0 to infinity, because no matter what numbers I put in here, as long as these numbers are positive, I can't get negative numbers here. No multiple positive numbers give negative numbers. Okay, so that's what all these graphs look like, and that's where they all come from. All right, some of your homework asks you to do just simple transformations graph, and it's been a while. We did that back in section 1, 2, I don't remember, 1.1 or 1.2. So let's perform the following transformations on the graphs. So here we are. So here, if I'm going to transform this graph, what have I done to it? I'm just taking x equals 2, and I'm going to move it over. I'm going to move it down 1, right? Because this is the same thing as 2x minus 1. So here, instead of and so I'm going to take my point, which is 0, 1. I'm going to shift it down 1. And then just kind of draw on my other asymptote real quick. Let me go to blue. I'll go back to blue. So that way it looks a little bit different than my actual writing or the actual note. So here. And so it'll come up from here, and then he'll go through this point, and then when it's at 2, it should go through 4. So 2 and then 4, so it comes up here, and then comes up like this. Okay, and so you can just roughly sketch these, and you're going to do this on your Web of Science, so you just click the right one. Here, what am I doing? Here, I'm shifting it to the left by 1. No, I'm not shifting it to the left. I'm shifting it to the right by 1. I forget. Horizontal, you always go the other way. When x is 1, it looks like 0. So I moved it over 1 here. And then I'm flipping it upside down. So it flips upside down here. So here is my point. This is still my asymptotic line. And it comes up and goes through like that. And it should come to 2. And then go up a little harder. Okay. And so just be careful, just like you move the point and then you flip it, and if you forgot all that, it's back in 1.1, 1.2. So you can just look at that. So there. All right, so let me leave this up for a second, grab a drink. All right. All right, let's get to this. So let's talk about the natural number. So the natural exponent and constant and exponential constant and function. So here, e is a very important number. It comes up all the time in exponents. And e is roughly equal to 2.7, and it's just irrational. It's just this huge, disastrous number, right? So I remember about 2.72. For most calculations, that's for most back of the hand calculations, that's fine. If you type in e, I think most programs use a double float saving of it, which is more than accurate for 99% of all principles. What e really comes from, e is really the limit if I take x of 1 plus x divided by x plus 1. If I just took the limit of this weird function, I get this. This is it. That is its definition. And we call this the natural exponential function, or e to the x, and it's sometimes known as the exponential function, since it has a ton of applications. So this is just a number. The graph of this is exactly like it would be one of these graphs, since it's 2.7, so it's greater than a equals to 1. We will not be dealing, as far as I know, we will not be dealing when your base is not positive, because if it's not positive, it gets weird, right? I don't even know if Desmos will graph it for us. So most cases are, I think, will be positive. Take off my watch. It says it's dying. I can charge as I'm sitting there teaching. Let's see if I can actually get it to. Yep. Yeah, it's not even graphing it. So the problem is once it's in real, there's nothing to graph, and because it gets too ugly. And can we do stuff with negative numbers, or can you take exponents of negative numbers? Yeah. Can you do it of complex numbers? And the answer is yes again, but that's definitely outside of the scope of class. We don't get into that until you're in like 432 and complex analysis. So, but here, so just know that your base, whatever the base is going to be between 0 and whatever, and it's going to be. So here, so that way, because you might ask me, what happens if a is 0? Well, don't worry about it. Or if a is 0, don't worry about it. What's a to 0 to any exponent is 0 to any exponent is 0, except if it's 0 to the 0, then it becomes definitely undefined. Where it just gets problems. So we're just not dealing with 0 or negative numbers. So if a equals a 0, here we can just easily identify this from the graph, right? And here, when we take limits of exponentials, as a goes to negative infinity, notice what it does here. It just goes off to 0, right? It goes to 0, and a goes to positive infinity. It goes to 1, and then when a is in between this, it's the opposite. It goes to positive infinity. When a is negative, when it goes to negative infinity, then it's 0. Okay, so this is that, and we'll actually do some sample problems finally, right? So let's do this. So let's take a bunch of limits of this. Make sure I'm not missing anything super fast. I wrote these late at night. I have a deathly afraid I might have forgotten something important. But I don't think I did. No, yeah, it's just graph a whole bunch of stuff. Graph, shift, graph, and then take limits. Perfect. All right, so let's do this. All right, so we're going to take x. I'm going to take the limit as this goes to negative infinity. Well, that's equal to the limit as x goes to minus infinity. And here, I'm going to alter this. And so here I'm going to have, so this is the same thing as 2 to the negative 1 times x, right? And then therefore I can use the exponential rule here. So I'm multiplying the two. So I'm going to use the exponential rule here to convert this into 1/2 x minus 1. Anyone confused of how I achieve this? Because this will be 2 to the minus 1 to the x power. And 2 to the minus 1 is equal to 1/2. So here I got this. Now, do I know what this is? Yes, I know what this is. Since a is less than 1 and 0, this I can just plug in to be 0. So I'm actually taking the limit now. Oops. Here if I no it goes to positive infinity minus 1, well that's just still positive infinity. Okay. Sorry. If this was positive, if this was positive, it would go to 0, but this isn't, so it just goes to infinity. So this is what this limit is. For here, we're going to take it to x to the goes to the positive 0 or the negative 0. Hold on, let me be clear on this. So how would we do this one? Well, we just do the same thing we've been doing before. So we take the limit as x goes to 0 infinity. And now we're going to push this limit onto this. So we can do that. So we can take the limit of e raised, and we're going to push the limit from here onto the upper part, 1 over x. And then we'll still need to take the limit here, but let's look what the limit does up here. Let's actually here, let me leave off the e for a second. Let's just look at this. So the limit as this goes to 0 from the negative side. Does anyone know what this limit is? What this limit is right here? Could you break it down so I understand? Number 3 or number 4? Sorry. Which one are we talking about? 3. Yeah, so here, number 3. So let me explain what I did right here. So here I have I have 2 to the negative x. That's the same thing as 2 to the negative 1 times x. So I just split, this is its coefficient, this is x. Since things multiplied by each other are equal to, so here I have multiples of each other, right? So 2 to the 3 to the 4th is also the same thing as 3 to the 2, 3 to the 4. And so I'm using this kind of in reverse, right? And so when I go back to that, I'm going to stuff this in and then raise this to the x power. So I put in the negative 1. 2 to the negative 1 is the same thing as 1 over 2 to the 1, right? Because anything negative from here, I have a negative exponent, I just drop it down. And if it's a 1, it just drops it below. I get this to the x power. So this turned into this. Once I did this, when I took its limit, since a is less than 1, and I'm going to minus infinity, it is equal to infinity. And so I get infinity minus 1. Well, infinity minus 1 is still infinity. Okay. Here, when I take this, when I take x to this, let's look at it. Let's look at it real quick. I have 1 over x, and I want to go to 0. Now, can I actually put in 0? Of course not. Doesn't work, right? 1 divided by x. But here, what does it look like? It looks like negative infinity, right? And so if I'm coming in from the left side, it goes to negative infinity. So this is equal to minus infinity. Okay, and so once I know this, I can rewrite this one right here is equal to the limit as t goes to minus infinity of e to the t. Okay, so I'm going to replace, so I'm just doing a variable replacement. I'm going to write, I know 1 over x goes to negative infinity, so I'm going to, when x goes to 0, from the left-hand side. So I'm going to rewrite this as and one of the things you can do is once I know this, I can just replace, I can set t equal to 1 over x, and then I have to rewrite this as well. I have to figure out where that went and then send t to that, okay? And so if I'm sending this to negative infinity, and it's e to the t, well, that equals to 0. Okay, and so the answer here is 0, as people put in chat. The answer here is 0. And so what do we do here? We took the limit of what's on the exponent real quick, figure out what that went. That limit went to minus infinity. Now, if I put negative e to the minus infinity, where the limit of it anyways is equal to 0. Now, for something more complicated like this, we do the same thing as I taught you to do last time. Instead of dividing by the highest, you still kind of divide by the highest power. And so in this case, the highest power here is e to the 2x. And so we're just going to divide everything here. So e to the 2x divided by e to the 2x of e to the 2x divided by e to the 2x plus 1 over e to the 2x. All right, so this evaluates to 1, this evaluates to 1. So here we have the limit as x goes to infinity of 1 over 1 plus 1 over e to the 2x. Well, where does this go? Well, that's important. So let's do a little bit of algebra on that real quick. So here I'll have still the limit as x goes to infinity of 1 over 1 plus e to the minus 2x. Is that going to help us? Sure, that'll help us. All right, but notice here that this base, right, this base is greater than e is indeed greater than 1. And if I go if this goes to infinity and I have a negative number, this is going to go to negative infinity. So this all goes to 0. So when I plug in this, it's going to equal 1 over 1 plus 0, which is just equal to 1. Okay. And so that's how you find the limits here. So the tricks here is just use these rules I've given you to simplify exponents into a way you can get it into something that looks like this. And notice here, and so here when I have this exponent, I'm just going to find the limit of the exponent, figure out where that goes, and then plug that in to get 0. And in this case, I get the x here. You can divide out by your highest exponential as long as you have the same base. And then when I get to this, notice if x going to negative infinity of a to the x is infinity, or up here, x goes to a to the x is infinity, and x to minus infinity of a to the x is 0. But if it's a to the minus x, I just switch these two, right? Because then I'd be going in the opposite direction. And therefore, this term, even though it's going to infinity, this is going to minus infinity. Well, minus infinity is indeed 0. Okay.